All right, let's look at an inclined plane problem. So the problem tells us that we have a mass m that is sliding down an inclined plane, and that mass is connected by a string to a second block over a pulley. So let's draw the diagram. So here we have an inclined plane, and we have a block of mass m, capital M, sliding down. It is connected over a pulley via a string to a second mass m. And the problem says clearly that the mass m, capital M, is moving down the plane. So we know that there will be an acceleration going down the plane. All right. So assuming that the string does not stretch and the mass's angle and coefficient of kinetic and static friction are known, what is the acceleration of the system? So since the string does not stretch, what that means is that as the block on the plane goes down, the block that's hanging will go up. And also they will have the same acceleration. So I'm going to draw the acceleration of block lowercase m as up. So the things that we know in the problem, I'm going to write those down. So the known quantities are mass capital M, lowercase m, the angle of the incline, I'll call it theta, the coefficient of static friction, the coefficient of kinetic friction, and I believe that is all we know. And what we're looking for, unknown, is in part A, we want the acceleration of the system, and in part B, now we're replacing mass lowercase m with a larger mass m1, so the system only moves up the plane if it is given a gentle push. And we're looking for this mass m1. We'll get back to this, but for now, I just wanted to write down the knowns and unknowns in the problem. So, in the first part, we are looking for the acceleration of the blocks. This is a classic example of a problem where we have to use Newton's laws because forces that act on these masses cause these masses to move. So let's start drawing the forces acting on mass capital M. Since it has a mass, of course it will have also a weight. So call this capital M G. Then since it is in contact with the incline, that means that it also has a normal force. So call this F sub n. We know that there is friction between this block and the plane, and since the block is moving with respect to the plane, that means that the kinetic friction is acting and not a static friction. Furthermore, since the block is sliding down the plane, that means that the friction will be opposing that motion, so it will be acting up the plane. So this is the kinetic friction. Okay? Now block M is also connected by a string. So that means that there will be a tension force acting on block M as well. So I believe these are the forces acting on block M. The weight, the normal force because it's in contact with the plane, tension force because there is a string that slows it down, that pulls it in the opposite direction, and the friction, kinetic friction, because we know that there is a coefficient of friction between the block and the inclined plane. Now, the forces that act on block lowercase m are its weight, and since there is a string that pulls it up, there will also be tension. Now, this lowercase m block is not in contact with a plane, so that means that there is no normal force acting, and it's also not rubbing against anything, so there is no friction. So these are all the forces that act on the different blocks. Now, we like to draw something we call free body diagrams, and I'm going to do that. So I will just use this dot as the mass m, and the forces that act on it are going to be the normal force, the tension force, the kinetic friction, and the weight. Now, very useful thing to do is to set the x direction, the positive x direction, in the direction of motion of the block. So set x direction in the direction of motion. So what that means is that going down the plane will be the plus x direction. Then perpendicular to it, we will have the y direction. So set y perpendicular to x. So that means that y is going to go perpendicular to the plane. So I'm going to draw that here as well next to the diagram. So this is plus x and this is plus y. So looking at the forces, we see that the normal force is in the positive y direction. The tension force and the friction force are both in the negative x direction because they are in the opposite direction of what we defined as the positive x. And then the weight is neither in x nor in y. So we have to break the weight up into components, and we want a y component. So I'm going to project this onto here. And we want an x component, so I'm going to project it onto the x-axis, like that. So this will be mgx, and this will be mgy. Now, the angle theta will be this angle right here. And that means that the y component of the weight will be mg cosine theta, and the x component will be mg sine theta. So now I can write sum of the forces in the x direction is mass times acceleration, and sum of the forces in the y direction equals mass times the acceleration in the y direction. But the block is not moving perpendicular to the plane, so that means that the acceleration in the y direction is 0, so sum of the forces in the y direction then will be equal to 0. So let's continue here with Newton's second law, see what the forces are in the x direction. So again, we picked the x direction to be down the plane, so in this direction. So that means that the mgx component is positive, and the tension and the kinetic friction will be negative. So I'll have mgx minus tension minus kinetic friction equals mass of the block times the acceleration. In the y direction, I have the normal force going up, so that is in the positive y direction, and I have the y component of the weight going down, so that will be in the negative y direction. So the two forces are F normal minus mgy is equal to 0. So now we said that mgx is mg sine theta. So let's look at why that is. So in this rectangle, mgx is equal to this side, and this side is opposite of angle theta. Opposite goes with sine. In this triangle, mgy is the adjacent to angle theta, which means that it will go with a cosine. So mg sine theta minus tension minus f sub k equals capital M times A. And in the y direction we have f normal minus mg cosine theta equals 0. So from here we know that kinetic friction force is equal to the coefficient of kinetic friction times the normal force. So from the above equation, we can see that the normal force is equal to mg cos theta. So that means that the friction is mu k mg cos theta. Now we plug in this force into that equation and end up with mg sine theta minus tension minus the friction force, so that would be mu k capital M g cosine theta equals mass times acceleration. So we have this equation in which we know capital M, we know g, it's 9.8 meters per second squared, we know sine theta because we know theta, we know the coefficient of kinetic friction, but we don't know tension. So we want to figure out what the acceleration of the block is, but not as a function of the tension force. So we can turn to the other block. So let's draw a free body diagram for the second block. So here is block of mass m. There is tension going up, and there is its weight going down. Now, remember that before we said that we will pick the positive x direction in the direction of motion of the block. But as we're pulling down this way, as the weight is pulling this block down, that makes this mass go up. So that means that for the second mass, the positive x direction will be up. So that's plus x. Let's write this on here as well, plus x direction. So now when we write sum of the forces in the x direction for block lowercase m equals lowercase m times the acceleration, the forces are positive. Well, we just have tension going in the positive x direction, so it's t minus mg, mg is in the negative x direction, equals ma. So in this equation, we know the mass of the block, we know g, but we don't know the acceleration and the tension. So looking at this equation and the red one that we boxed, we have two equations and two unknowns. We are looking for the acceleration, so how about we solve for the tension in this equation and plug it into the other one. So tension here is going to be mg plus ma. So now going back to the previous equation that we boxed, mg sine theta minus the tension, so tension is mg plus ma minus mu k, that's okay, capital mg cosine theta equals capital M times acceleration. Looking at this equation now, we see that all of our quantities here are known except for the acceleration, and that's what it is we are trying to solve for. So mg sine theta minus mg minus ma minus mu k mg cosine theta equals uppercase ma. I'm going to add lowercase ma to both sides. So mg sine theta minus lowercase mg minus mu k mg cos theta equals ma plus lowercase ma. I can factor the a out in here and get mg sine theta minus mg minus mu k mg cos theta equals capital M plus lowercase m times a. Let's stop a little bit and see what all of these forces mean. Mg sine theta is the weight component in the x direction, which is pulling the block down. This negative mg is the weight of the block that's hanging. So what this is saying is that the weight of the heavier block is being slowed down by the weight of the smaller block and the friction. So as a result of the heavier block having a component of the force along the x-axis and the lighter block and also the friction opposing that, the system, which is the two masses combined, will have a certain acceleration a. So now we solve for the acceleration, and that will be mg sine theta minus lowercase mg minus mu k capital mg cos theta divided by capital M plus lowercase m. If we had any values, we would plug those in, but we would get, this is actually the final equation that we need to use to solve for a. All right, in part B, now we have a different situation. So what we know in part B is that we still have this incline. We have block M. We have a different block, M1, and the system is at rest unless we give the system a push, and in that case it will start going up the plane. So let's look at the forces that act on the block on the incline. So there is the weight. Now the block is in contact with the incline, so there will be a normal force. The block is held up by a tension. And then there will be a friction force acting in the system. Now, what type of friction force are we dealing with? It is the static friction, because the block is not moving with respect to the plane. So now figuring out the direction of the static friction, the problem says that if we give the block a bump, then it will slide up the plane. So the static friction then is going to be in the opposite direction of that motion. So static friction is down the plane. All right, now the forces acting on mass M1 are its own weight, M1g, and its tension. All right, so let's draw a free body diagram for mass M. We have the weight going straight down, tension up the plane, the normal force perpendicular to that, and static friction opposing the tension. So if we gave the block a push, then the block would go up the plane. So we'll pick the positive x direction in the direction that the object would be moving. So that's our positive x direction. Perpendicular to it, we have plus y. So these are the two directions that we're going to have to break forces up in. And if we look at our diagram, tension is in the positive x, static friction is in the negative x, normal force is in the positive y, and weight is in neither. So I'll have to break the weight up into components. So this will be mgy, and in the x direction we have mgx. So now the block is not actually moving. We would have to give it a little push for the block to move. So Newton's second law says that sum of the forces is, capital M mass times acceleration, but the acceleration is 0 because the block isn't yet moving. So mass times acceleration is 0, sum of the forces is 0. So going up the plane in the positive x direction, we have the tension force. That's not the tension force. This is. And then down the plane, we have the static friction, and mg in the x direction, we determined that that was the sine theta component. And sum of these forces is equal to 0. In the y direction, so sum of the forces in the y direction is 0 because the block is not moving perpendicular to the plane. And the forces in the y direction are the normal force and mg cosine theta. So those forces equal 0. That means that we can solve for the normal force, which is mg cosine theta, which means that we can solve for the static friction, which is mu s Fn. So it is mu s mg cosine theta. So now if we plug in the static friction in the previous equation, we have tension minus mu static mg cosine theta minus mg sine theta equals 0. All right, so we have this equation for the first block, and we see that there's a tension force that we don't know. We know the static friction, the coefficient of static friction. We know the mass, capital M. We know G, we know theta. So we are looking for mass M1, which means that this equation is not helping us at all. So let's look at the other block. So drawing a free body diagram for the other block, we have M1G going down, and we have tension going up. Now, remember that we said that we pick the positive x direction to be in the direction the block would move, the block on the inclined plane. Well, that also means that the positive x direction for this block M1 will be down. So this would be the positive x direction for block M1. So that means that when we write sum of the forces for block M1 equals M1 times acceleration, which acceleration is 0 because the blocks are not moving at all, the positive force here would be M1G, and the negative force would be the tension. So M1G minus tension equals 0. So I can solve for the tension in this equation. So tension is M1G, and here is my variable that I'm trying to solve for. So I will plug this into the previous equation. So instead of T, I'll plug in M1G, and then I have minus mu static mg cosine theta minus mg sine theta equals 0. And I'm solving for mass M1. So M1 is mu s capital Mg cosine theta plus mg sine theta divided by lowercase g. And if I look at carefully, all of these terms have g in them, so m1 will be mu s m cosine theta plus m sine theta. And this will be the mass necessary to make block capital M move up the plane given a gentle push.